Statics, type 3, freely hinged. So in 2006, question 7a, we had a uniform rod of length 4 meters, which is free to turn around a vertical plane about a hinge at P. We're told that the mass of the rod is 20 kilograms and that the rod is supported in a horizontal position by a rope which is attached to Q at a point 3 meters vertically above P. So basically that's holding the rod PQ in place where the hinge is at P. So what we want to do here first of all is to find the tension in the rope, and then we also have to find the magnitude and the direction of the reaction at the hinge. So if we were to look at the forces acting on this system here, what we have is our hinge at P. So we're going to have our X and our Y components for the reaction at P. So we'll be finding the resultant of that for part 2. We're going to have the weight of the rod PQ acting in a downward direction. And then we have a rope holding the rod PQ in place. So therefore we're going to have tension acting away from Q along the rope. So these are all the forces acting on our rod PQ. So we also know then that we have the length of the rod, and the position in which the rope is attached to the wall is 3 meters directly above. So if I mark that in green, so we have 3 meters, and then we have 4 meters. So this information is going to be useful because if we look at that, we can see we have up, down, left, right, but this tension is a bit of a problem. So that means we're going to have to resolve our tension into its parallel and perpendicular components. So if I look at the angle at which the rope is with respect to PQ, if I call that angle T, then what I can do is I can take this tension and I can resolve it. So if I use a different colour, well, we can say that the tension acting upwards will be T sine theta, because that's the opposite to the angle theta. And then the horizontal component will be T cos theta, because that's the adjacent in our right angle triangle. Now, what's interesting is that because we were given the vertical height and the length of the rod PQ, I can take this triangle out, and I can work out what sine theta and cos theta are. Because if we know that this side is 3 and this side is 4, well, we recognise that as our Pythagorean triple, 3, 4, 5. In other words, the square root of 9 and 4 squared, 9 and 16 is going to be the square root of 25, which of course is 5. So therefore that gives me 3 is the opposite, 4 is the adjacent, and 5 is the hypotenuse. So because sine theta is equal to the opposite of the hypotenuse, I can therefore say that sine theta for this question is going to be 3 over 5. And because cos theta is the adjacent over the hypotenuse, then that means that cos theta is 4 over 5. So now, if I look at my first law of coplanar forces, we have the up force must equal the down force, in which case then the up force is y and t sine theta, and that must equal my down force, which is the weight of the rod. But we know that weight is equal to mass times gravity, and because we were given the mass of 20 kilograms of the rod, well, I can therefore say that this is now going to be written as y plus t, and sine theta is 3 over 5, and weight is going to be mass times gravity, so in other words 20 times g. So that's my first equation. The second law of coplanar forces is that my left forces must equal my right forces. So I can therefore say that x must equal t, and my right force there is cos theta, which we said was 4 over 5. So in other words, X must equal 4/5 times the tension. And my third law of coplanar forces is that the sum of the clockwise moments must equal the sum of the anticlockwise moments. So therefore we need to decide, where are we taking our fulcrum? So because we have reaction forces at P, so it was easier to eliminate those reaction forces. So we're going to say fulcrum at P, and therefore that means that X and Y have no moment because their perpendicular distance will be 0. So they're at the fulcrum. So if I look then at my other forces and see which is turning it clockwise, which is turning it anti-clockwise. So I can see W is pulling down on the rod, so that's going to pull it in a clockwise direction. And then if we look at T cos theta, well, that has no perpendicular distance because it's along the line of action to the fulcrum. So therefore T cos theta has no moment. So therefore the only other force is T sine theta, and therefore that's going to have a anticlockwise moment. So again, I can get my perpendicular distance from Q to P. So because our moment is our force by our perpendicular distance, and if I look at W, I can easily work out my perpendicular distance here. I can see it's going from halfway along PQ, in other words, from the center of the rod, which is going to be 2 meters away from P, because the rod length is PQ. So therefore the force is W, and the perpendicular distance is simply 2. And that must equal the anticlockwise moment, which is T sine theta. And because T sine theta is acting directly up at Q, well, the perpendicular distance from Q to P is the length of the rod, which is 4 meters. So therefore that's going to be 4 times T sine theta. But of course we know that W is the weight, which is 20g. And we know that sine theta is 3/5. Well then, by simply rearranging there, I have 40g is equal to 12/5t. And therefore I can say, well, the tension must be 50g/3. So that's the first part of the question done, because we're looking for the tension. So we have 5 marks for setting up our moments equation and 5 marks for solving for T. And then obviously for the next part, we're looking for the magnitude and direction of the reaction at the hinge. So we've already found Y in terms of T here, so I can rearrange and sub in for T, so that'll give me Y. And we have X in terms of T. So we can use these 2 equations now to work out what Y and X are. So basically Y is going to be 20g minus 3/5 T. But we've just found out that T is 50g/3. So in other words, Y is going to be 20g minus 10g. And therefore Y is equal to 10g. So that's subbing T into 1. So if I sub T into 2, well, I can say X is 4/5 times T, but T is 50g/3. And therefore that gives me 40g/3 for the reaction force X. So of course I don't want X and Y, I want the magnitude and direction. So in other words, if I look, there's Y, and there's X, and that's at the hinge P. So I'm looking for the resultant here and its direction. Okay, So therefore, all I need to do is Pythagoras, because if I complete my parallelogram there, or the right angle, I can therefore say that the magnitude is going to be the square root of x squared plus y squared by Pythagoras. So x is 40g over 3, and y is 10g. So if I simplify that, I end up with square root of 1600 over 9 g squared plus 100 g squared. And then simplifying that gives me 50g over 3. So that's my magnitude. And now we have to find our direction. So our direction is always just going to be opposite over adjacent. So in other words, y over x. So y is 10g over x, which is 40g over 3. And that gives me tan theta is equal to 3 over 4. And therefore theta is tan inverse of 3 over 4. So the direction is 36.87 degrees. So for getting x and y, we had 5 each. And then for getting our magnitude and our direction, so for both magnitude and direction, it was 5. So we had 25 marks overall. So nice question that.